So let's see an example of such a proof on this code, which finds the maximum of an array in the obvious way. You step through it and you keep track of a maximum of a prefix of the array. That's intuitively what the code does. For a formal proof, we have to find a loop invariant. So I've already done that job for you. And the loop invariant consists of two parts. It will be useful to give them colors. I hope that these are distinguishable no matter what kind of limited color sight you might have. So this is a little lighter than the other one, right? Is red and blue, in case that helps. So the first thing we have to check, we have to go through these three conditions and show that each is satisfied with the loop condition that we've chosen. The first condition says the loop condition holds before the loop. So I marked in the code these 4 positions A to D. So let's have a look at this first part. If we look at position A, we've just initialized things so that I is 1. So if you look at what the loop invariant really says here, I'm just copying this and insert what the value of I at this point is. I mean, this takes a lot longer to write than to think through. If you put I minus 1 here, so this is just 0 up to 0. It's the set with just the 0 in it. Well, the second bit is not very interesting if we insert 1 here. That's something that we assumed in the loop. So we call the function with an array that has at least one element. And so that part is what guarantees this first bit. I should have done this in red, I guess. Sorry, light blue. I'm not that colorblind, but. So that guarantees the first bit of the loop invariant just by assuming it at the beginning of the function. And that's something you often have to do. Now for the second bit, we can just rewrite this. So the second bit, that maximum doesn't really do anything, right? It just insert this. It takes the maximum over a set that contains a single value. So the maximum will always be that single value. So all we're saying here, this part on the right is really just A of 0. So the claim that we're making is the current max is the value of A of 0. And that's exactly how we've assigned it just before that. So that's also fine. Okay? So that was the somewhat easy bit because it didn't really involve the loop yet. I'll try to have the code on the slide as well as my writing. It's going to be a bit of a challenge. For the second part, we need to show that the loop invariant and the condition of the loop, so that's this fact that I is strictly less than n, these two things together at B guarantee that we have, again, the loop invariant at C. So that's an implication, right? And we talked about last time at length how you can prove, how you can possibly prove implications. We talked about all these different proof templates and so on. So that's applicable here. Now, in this case, the most convenient bit is to do a case distinction first. And the reason for that is that inside the loop, there's an if. So there's really two things that can happen depending on whether the if is taken or not. So it's quite natural that we want a case distinction based on whether or not this loop condition is, this if condition is true. And we'll look at those two cases separately. So a first case would be that this is true. Which means intuitively that we found a new minimum, a new maximum. Right? So the new element we're looking at, we're taking into account now, is bigger than what we currently had as the maximum. Now at this point, we use what we had in the premise. We're proving an implication, so we can assume what's on the left side of this implication arrow. In particular, we know that at the position B in the code, here, the invariant I was true. And conveniently, that's just after where we, just before where we are in the code now, if we're looking at this if. So using the red part of the loop invariant, we can use what we know about current max. Namely, that current max so far is the maximum of this expression, like just up to I minus 1. If we're in this case, then the if statement is true and the then branch is executed. So we assign current max and we set it to A of I. Now, what does that mean for this red statement of the loop invariant? We can already have a look at that. Let's start with the maximum. What that means is I can now extend the range of this maximum in the loop invariant for one more index, and it will still be true. Because we've seen the current maximum, so the maximum of the elements up to position I minus 1, that was current max, but AI was even bigger. So clearly AI is the maximum of everything up to position I. It's just rephrasing this again. This is almost like the next loop invariant that we need, except that we're not yet at position C. Instead, we've only executed line 9 so far. So what happens in line 10 is something that changes the value of I. We make I1 bigger. So that means in the loop invariant, we have to adjust the value of I. If this was true before, then if we now make I1 bigger, we have to make it in the statement 1 smaller to compensate for that. So this, again, this is true at or after line 9. And so once we set I to I plus 1, we'll have the same thing, but with an I minus 1. Because this is now actually one bigger, okay? And now if you look at this, that is exactly the red part of the loop invariant. It's character by character the same thing. And also after line 10, I mean, should have stressed this, that's really at C. It's the same position. So that in that case, so that's often how a proof goes. So zoom out a bit, right? We're we're proving the second part of our overall claim. And within that claim, we're in the first case of a case distinction. And within that case, we've proven that the red part of the loop invariant holds again at the bottom of the loop body. So next, the blue part. What can we say about the blue part? We know at B that the loop invariant was true, but we know more. We also know that the condition was true. So the loop condition, otherwise we would have left the loop. So at this point, I was strictly less than n. The loop invariant only says less or equal, so this strictly less is stronger. I don't know. I'll mark this with red and then mark this with blue. I don't want to write it in blue because the contrast is not that great. So this was true at B. Actually, no matter what happens in the if statement, that doesn't touch I, but we'll always increment I afterwards. So by the time we get to C, we'll have made I 1 bigger. So we can only say that I minus 1 is less than n. But that still implies that I is less or equal n because it's integers. And so that finishes the blue part. And I think we can move this outside of the case distinction because it's the same for both cases. So I'll move this down here and out of the case distinction. We have to do our case 2 though, which was that the if statement is false, right? This one. In other words, A of I is not bigger than the current maximum. In that case, we don't execute the if statement, right? But we still have to argue for the red part to be true at the end of the loop. So we don't touch current max. However, we know something. We know that the previous maximum is at least as big as this next element. So we can again extend the range of the maximum by one more element. So from this statement, we know if we take our maximum and go from 0 up to including I, then that is still the value of current maximum. We haven't changed it. It's fine if we have this tie, if the next element is another occurrence of the maximum. So it's fine, we can still pick the first one. And the rest is really by the same arguments. So this is after line 9. And so after we incremented C, I, we do the same step. Let's say the red I holds. At C. Okay. Notice that we're basically following the structure of the code, but we're also following the definition of a maximum. It's either if you add one more element, either that element is a new maximum or it's not. That's all that happens. So that finishes the proof of the red claim in both cases of the case distinction. And we could get rid of the case distinction for the blue part because it behaves the same in both ways. Taking those two things together, that proves that I holds at position C at the end of the loop body. Okay, and that was this part. So that finishes. I could have ticked this off. We've done that here, done that now. What's left is the Roman third, which is that the loop condition actually does what we want for the post statement, for the post condition. And for that, it's basically sufficient to spell out what that is. And I'll spare you another round of me typing this, copying it. So that's the 2 bits of I, but then we also have not the condition. The condition was that I is strictly less than n. So not the condition is I greater equal n. Mark that here. Okay, you remember? And so if you look at this, I copied the wrong thing here. This was from condition 0. There's no point if you can't read it, right? So if we're at this point, then we take the last 2 conditions. Okay, again, shouldn't have copied this. This was an I. I inserted the 1 there. These 2 things together obviously mean that I is equal to n. And then if you insert n in here, you get the statement that current max is the same as taking the max over the entire array, because we're letting k go from 0 up to n minus 1. So this is true at the end of the code, and intuitively that's what we wanted, because that's the maximum of the array. Okay?